Okay, sorry, I had to pause it. I realized I messed something up, so I wanted to delete it. So, okay, all right, so let's take a look at the formula for a bomb calorimeter. So, a bomb calorimeter is Q equals C, which is our specific heat, times the change in temperature. And the reason we don't have mass here is because the specific heat in this case for bomb calorimeters are joules per grams degrees Celsius. So when it cancels, the Q will still be in joules. Okay, so that's just a little difference there that we haven't done before. Okay, so let's take a look at down here about specific heat. So if something has a high specific heat, something like aluminum, the higher the specific heat value, the harder it is to make it hot. Like if you think about a can sitting outside in the heat and you can grab it at the end of the day, it takes a lot of energy to make it hot. So this is going to be the higher the specific heat, um, the lower the temperature change when heated, because it takes a lot of energy to do it. Whereas the lower specific heat, something like copper, the reason pans are made with copper is because it gets hot quickly. So this is going to be the higher temperature. Okay. All right, let's relate delta H and Q because these values here gave us Q and we talked about measuring delta H. So how can we relate them? Well, Q equals, if I say delta H equals, it's Q divided by the moles of the substance. Okay, so you have that there. And there'll be negatives to consider here. I didn't put in negatives on this part because it depends on the situation, and I'll explain that as we go through some problems. Okay, so let's take a look at problem number 3 here. It says the overall reaction in a commercial heat pack can be represented as the following, and it gives us delta H value. You should notice that this is exothermic because it's negative, and indeed it's asking how much heat is released when 4 moles. Well, our reaction here is 4 moles, so how much heat is released? It's 1652 kilojoules. Okay. If they asked for the delta H value, you could put the negative, but since they're already saying released, I wouldn't put negative again. That's just kind of redundant. Okay, how much heat is released when 1 mole of Fe2O3 is produced? Well, you see here we have 2 moles produced. So you're just going to take the value here and divide by 2 for that one because we want it in terms of 1 mole. Now, C is a little more involved, and I don't really have room for it, so I'm going to move my paper, and I'm going to do it on the sheet of paper. So for C, we say that it says, how much heat is released when 1 gram of iron is reacted with excess O2? So we have 1 gram of Fe. You know, in chemistry, we never work in grams, so we're going to convert to moles. So 1 mole of Fe is 55.85 grams. Okay, and then we want it in terms of how much heat. So we need to look at our reaction. So how many moles of iron do we have in a reaction? If we look back here, we have 4 moles. So when we move this out of the way, we have 4 moles Fe. And for 4 moles of Fe, we get negative 1652 kilojoules. Okay, so then we need to calculate that, multiply and divide, and I get negative 7.39 kilojoules. Okay. All right, same issue as far as space goes for D. So I'm going to put it here. So D, how much heat is released when 10 grams of Fe and 2 grams of O2 are reacted? So this is like a limiting reactant problem because we don't know. It's going to be whichever one gives us the lower value here. So we've got to compare. So let's first start with our 10 grams of Fe. And again, we do not want to leave it in grams, so we're going to change to moles. So 1 mole of Fe, 55.85 grams. Okay. And then what are we going to do after this? Well, we're going to compare the Fe to the O because we have to figure out who's the limiting reactant. So in our reaction, we have 4 moles of Fe. And we have, I'm sorry, I didn't mean to say Fe to O. I meant Fe to the product. So we have to compare these guys. Okay, so we have 2 moles Fe2O3. Okay, and we'll calculate that. And when I calculated that, I got 0.0895 moles of Fe2O3. And again, the one that's a lower one is the one that we're going to choose to work with. And then we get, the other one is 2 grams of O2. So 1 mole of O2 is 32 grams. And then I've got to compare the O2 in the reaction. So I have 3 to the product. So 3 moles of O2 is 2 moles of Fe2O3. This all should be reviewed for you guys. And on that, I got 0.125 moles of Fe2O3. So that should indicate to you right there that our limiting reactant is the iron. Okay. So what do you do from here? Well, if we know it's this many moles that we can produce, we want to know how much heat's released. So we can just set up a proportion. We can say 0.0895 moles of Fe2O3 produces X kilojoules, whereas in our reaction, 2 moles produces negative 15 or 1652 kilojoules. And you just cross multiply. Okay. Oh, sorry, I didn't realize you couldn't see that. So you set it up here. So we have the moles that we got in our thing up here for our limiting reactant per kilojoules we don't know. And then this comes from our reaction. 2 moles is negative 1652. Okay. Okay, before we begin the next problem, I need to write down some specific heat values. So I'm going to have this, so we'll have it as a reference. I mean, this is the type of stuff you'd be given on a question. So I want to just put it on the board. So specific heat, and this is joules per grams degrees C of these different substances. So for H2O liquid, we just said it was 4.184. Some people do use 4.18. For H2O gas is 2.03. And again, these will vary a little bit. Sometimes you'll see different numbers. This is what I'm going to use right now. Just use whatever's given. And then for aluminum solid, I know it looks like not like aluminum, sorry, it's 0.89. Then for iron solid, it's 0.45. And then mercury, which we know is a liquid at regular temperatures, 0.14. And carbon solid is going to be 0.71. Okay, so those will just help us so we have this problem. Okay, so it says, consider the substances in table 6.1. Well, those are the substances. This is table 6.1. Which substance requires the largest amount of energy to raise the temperature of 25 grams of substance from 15 degrees Celsius to 37 degrees Celsius? So we just said when we look at the specific heat values, the higher the value, the harder it is to make it hot. Okay, so obviously we need more energy. I'm just going to put this. So I'll put more energy when we have a higher specific heat value. So who of these would you say? It's obviously liquid water. Okay, that takes the most energy to raise the temperature of, which makes sense. Like when you think about oceans and stuff like that, it really takes a lot of heat energy to raise the temperature of the water of the ocean. Okay. All right, so let's take a look at the next part of the question. It says calculate the energy. We have to calculate that energy. Okay, so we're just going to calculate that. We're going to use QMCAT. Q equals MC delta T. So Q equals, they gave us a mass, is 25 grams. The specific heat, we're going to use a liquid water, so 4.184. And what is our change in temperature? It is 37 minus 15. I'm just going to put that in there so you guys can see all the part. Okay, and when I calculated it, I got 2301.2 joules. And then I think it was asking, calculate the energy. The later question's asking about something in kilojoules. So let's just convert this to kilojoules. And remember, 1,000 joules equals 1 kilojoule. So this should be 2.301 kJ. Okay. All right, so let's read the rest of the problem. It says, which substance in table 6.1 has the largest temperature change when 550 grams of substance absorbs 10.7 kilojoules of energy? Well, now we're talking about the highest temperature. So highest temperature change means the lowest specific heat. So who will be the lowest specific heat here? It looks like it's mercury, right? So we're going to be dealing with mercury. So now let's do the same thing. So let's calculate. They told us, it says the substance absorbs 10.7 kilojoules. So we have 10.7 kilojoules. We know we cannot plug in that to the Q equation because Q is in joules. So we're going to me just change this so you can see it. Okay, good. All right, so we're going to have to change this to joules. So this would be, we're just going to move the decimal place 2 times like that. 3 times, sorry. Right, 10.7, 3 times. Yep, so that's joules. Okay, our mass is 550 grams. Our specific heat, we're going to use mercury, so it's 0.14, and we don't know our change in temp. So we're just going to solve for that. And when I solved for that, I got 138.98 degrees Celsius. Okay. All right, I'm going to pause it so I can get a different piece of paper for this. Okay, now we are in question 5. So let's read question 5. It says a 5-gram sample of one of the substances listed table 6.1 was heated from 25.2 to 55.1, requiring 133 joules. To do so, what substance was it? So this is, we're just trying to figure out what would give us those values. So we know that it told us it's 100, I'll put here, it's number 5, 133 joules. They told us how much, right? We have 5 grams, is that? Yeah, 5 grams, sorry. We don't know the specific heat because that's what would give us the identity of substance. So we're putting that there. And then our change in temperature is 55.1 minus 25.2 degrees Celsius. So when you solve for C, that gives me 0.889 joules per grams degree C, which if I look at my list from before, let me see if I can find it in all my papers. If I look at my list from before, that indicates that it must be, oh, you can't see it. It must be aluminum. Okay. Okay, so now we're going to start to look at a little more complicated problem. In this type problem, in number 6, it says we have a 150 gram sample of metal. It's added to 150 grams of water. So we used to do a lab like this where you'd have water in a cup and you take the initial temperature. Here's our thermometer. And then we put a piece of, we boil a metal in water, and then we put that metal in here and see what happens to the temperature. Okay. So in this case, we are using QMCAT, but we have to use it twice because we're going to have MC delta T for the metal. Because if you think about it, the metal is transferring its heat to the water. And then we're going to have MC delta T for the water. Okay. So let's see what we have here in our, we have 150 gram sample of metal. So this would be 150 grams. The specific heat of the metal, we don't know because we're trying to figure out what metal it is. So this is an unknown. Our change in temperature of the metal. Now it says the metal went from 75 and then it went down to 15 because the water became 15. So they both became 15. So 75 minus 15. And then the mass of the water, it was 150 grams of water, incidentally. Same thing. And specific heat of liquid water, we're going to use 4.18. I'm going to be lazy here and not put the 4, whatever. And then our change in temperature is, it says that the water rose to 18.3 degrees Celsius minus what it originally was, which was 15. Let's see, rises to 18.3. Okay, so you would just solve for that. And C gave me, when I calculated it, 0.24 joules per grams degree C. So if I look at my little table again, I'm going to try to decide who that is. And if I do 0.24, in this table, it's closest to mercury. It's not a great measurement. Okay, so as I was looking at that and noticed that none of them matched, I did notice there's an error, and maybe you guys caught it. But if you think about it, the metal, when you transfer it, the metal started, it said, at 75 degrees Celsius, and then it's added to water at 15. Well, the end temperature of the metal and water are going to be the same. So this, in fact, should not be 15. This should be 18.3. So I'm going to cross this out, and we need to calculate it again. So I'm going to pause it. Okay, so I recalculated it. It's still close enough. It's still 0.243. So, it's again, it's not one of our substances probably on our list, but I don't think it even asked us to compare it to the list. So there's that. Okay, all right, let's move on. Okay, in question number 7, now we're dealing with a coffee cup calorimeter again, but we have some different things going on. We're not just adding like a metal. It says that we have 50 milliliters of a 0.1